Bismillahirrahmanirrahim. The topic today is assembly, and what you see here is part of a 2D mesh simplex element. Two simplex elements are visible here, but it is assumed that there are other elements too. For the two elements shown, let's assume we have these stiffness matrices. These are in uh, these two matrices are for element 2 and element 7 respectively, and these are elemental matrices. Now we want to assemble these two in the global matrix, and obviously there are other there should be other matrices as well, but we'll just illustrate using two. Now why we are using 2D mesh is that 1D is very tedious, it's very obvious, and doesn't tell us much. It's not hard to do either. As for 3D, it becomes out of hand when you want to do it manually. Otherwise there's no difficulty there, but to illustrate, 2D is the best, and once you understand how to assemble 2D system, you can also assemble 3D. There's no further difficulty there, except the fact that these matrices are very big. Now, does this size make any sense? K2, you have 6 by 6. So does it make any sense? Yes, because for each element you have 3. For element 2 or element 7, you have 3 nodes, and each node has 2 degrees of freedom. For example, if we talk about this, so the degree of freedom, you have U5, V5. Similarly, U2, V2, U1, U1. So there are 6 degrees of freedom, and then you have 6 degrees of freedom per element, then your U as well as your F matrix. And what I'm talking about here is this. If this is 6 into 1 and this is also 6 into 1, then this has to be 6 into 6. So it makes sense. We are talking about stress analysis problems. Now, for 3D systems, obviously the size will be much bigger. Otherwise, what we are going to learn today holds for 2D, 1D, 3D, every kind of system. Now we assume that this KE has been obtained already, and you know how to do it. We have spent some time discussing that. For a 2D simplex element, this matrix is obtained simply by this calculation. Please review your material where we discuss the calculation of elemental matrices. Now we can go one step further. Some of these things are given to you. T, for example, thickness, A, these can be calculated easily. What about B? You know, the B matrix, just as a reminder, B matrix is for a 2D simplex element. It is, if you recall, BI0, BJ0, BK0, 0CI, 0CJ, 0CK, CIBI, CJBJ, CKBK. For 2D, it's as simple as that. And you have similarly you have expressions for D matrix, which will be different for plane stress situation and plane strain situation. So you get this, you have recalled how to calculate these Ks. So we are not going to calculate Ks from data given, although in this case we cannot, because we don't have the values for coordinates, but for any problem you'll have those values. So to calculate these two, this is not difficult. Now if we have these two and we want to assemble it in a global matrix, what should we do? That is the topic for today. So we need to assemble the system matrix, not the elemental one, but the system matrix. Now we'll just illustrate using these two elements, but you understand that there could be other elements also. So let's start. First of all, what about the degrees of freedom? Now degrees of freedom, it's very easy to figure that out. If you take this, for example, this is element 2. First let's take element 2. Now the asterisk means this is the I node, and because there is a convention that we always go like this counterclockwise, so if this I is specified, then this is J node and this is K node for element 2. We are talking about element 2 here. Now what degrees of freedom correspond to these values? It's not difficult to see, because for 2D, if you recall the connectivity, if you recall what we have always been talking about the connectivity. So connectivity means that we have for 2D system 2ai minus 1, 2i, whatever the node is. If this is, we're talking about this one, then the degree of freedom between this for this system is not exact. For example, node number and degree of freedom is not exact, the association. Now if one for 1D, if it's node 1, then it's element 1. If it's node 2, then if it's node 1, then degree of freedom 1. If it's node 2, then it's degree of freedom 2, because each node has only one degree of freedom. Here we don't have that situation. So this node 1, this node 2, it will have 2 degrees of freedom. So when we come to this, then we have to compensate for that. So this node 1, this has to this one, this has to have the degree of freedom 1 and 2, this 3 and 4, this 9 and 10, because each has 2 degrees of freedom. So the formula that specifies all that is simply this. You just put in the node number here. Now if you do that, then for this 2, node number 2, so put 2 here, 2 into 2, 4, 4 minus 1, 3 and 4. So this 2 corresponds to degree of freedom 3 and degree of freedom 4. Similarly, node 1, similar formula. Now you put value of 1 here, so you get 1, 2. For 5, same formula, 9, 10. So you have this nicely specified. Similarly, the same sequence has to be here. Now there's no difficulty about this, should be no difficulty about this, because once you specify that I node is this one, then the rest, this is number 2 is I, then J is 1 and K is 5, because you always follow this convention of counterclockwise. So these numbers must be in this sequence. When you mesh them, the moment you mesh them in this kind of a scheme, and then the values you get, they depend on this scheme. So if you change the sequence here, there'll be a problem. Similarly for K7, now for K7, this is I node and this is J node. Now this 5 node was K node for this element, but J node for this. There's no problem, there's no difficulty here, because again you have to, each element is different. It's I, J, K. So if you talk about the connectivity, the mapping from the node number to the degree of freedom, then it's I node, then you need, again use the same scheme, 2 into 4, 8 minus 1, 7 and 8. So you must have this 7, 8, then J node 9, 10. You have 9, 10 here, and then K node 1, 2. And similar numbering here. So it's symmetric, the system has to be symmetric. So this is how you specify the degree of freedoms at the elemental level. Now what remains is very simply mapping system matrix. Now let's assemble that. First of all, we must create a placeholder, and by placeholder I mean all the degrees of freedom that are likely to appear. Now in this case, we know that at least till 10 we have, from 1 to 10 we have, and it's reasonable to assume that if there are other elements around here, because this system is not just 2 elements, so if there are other elements, then there'll be other degrees of freedom too, but at least till 1 to 10 we have. So let's create a situation where we can hold these, and this means that there could be others. Similarly, horizontally, and similarly there could be others. Now what remains is very simple. Let's talk about this number 22 here. Where should it come? Now, for in the elemental scheme, it is at 3 3. So no points for guessing where it should come here. 3 3. This is 22 here. As simple as that. Let's talk about some other element. For example, what about 30? This comes at place 1 1 1 and 1. So again 1 1. Now let's take another example which is not a diagonal entry but an off diagonal entry. For example, let's talk about this -2 here, and because it's a symmetric matrix, it's also here, has to be here. Now this place is, if you can call it 310, and this place is called the location is 10 3. You always call the row first, so 10 3 or 310, because it's symmetric, both must have this value -2 and 2. So we talk about 10 3 first, and this is 10 and this is 3, so you have -2 here. Similarly, if we talk about this one, this is 310. 310 means you extend this 3, and here you have -2. So you keep on filling these entries from this to this, and it takes a long process. I'm not going to show you every entry shifted, transferred from here to here, but you get the picture. Now there's just one point to explain here, and then we can move on, and that point is there'll be some entries where you'll have a repetition. For example, let's take this -8, this one. This is 210, and obviously when I talk about this, then it's 10 2 also. But let's say first we take 210. This is 2. Keep. This is 10. So this is -8. This has to be here. And obviously when I talk about symmetry, then this 2 and this 10. So -8 is here as well. That goes without saying, because if these are symmetric, then the final case also should also be symmetric. So whatever you add at 10 2, it has to be at 210 also. So that goes without saying. Now this one is -8. Now if we talk about this 210 position, then there's an interesting thing to note here, and that thing is that you have for example in this second element also the 210 position is occupied. For example, this 2 and I'm sorry, for this you have yes, this 2 and this 10, -4. And similarly for 10 2 also, this one. So if you talk about 210, then -4 has to be 210 for K7 also. But 210 is this position, so we already have point -8 here. No problem, you just add -4 here. Here they will be added, and the same goes for here. So first of all, you map all these elements from all this entries from this to this, then you come to this point to this element, and then again do the mapping, and at some places you'll have this doubling. And what are those places where you have this doubling? They are the places where you have common nodes. For example, in these two elements, the node 1 and node 5 are common. Node 2 and 4 are not common, they are separate. So wherever you have 2 or 4, and 2 and 4, degree of freedom for 2 and 4 are, you know, the 3 4 and 7 8. 3 4 7 8, there's no repetition here, there's only 3 4 here, 7 8 here. But if you talk about this 1 2 degree of freedom and 9 10, 1 to 9 10, and here also you have 1 to 9 10. So wherever these degrees of freedom occur, where there's a connectivity, then you have addition, and that is very much in line with what you have done already for 1D systems as well. So that is all there is about assembly of K matrices. And you keep on, you first transfer all these entries here, then you transfer all these entries here. There will be some repetition also. Repetition, by repetition I mean there will be some points where you have to add them together, but that is no problem. And the net result will be your K matrix will still be symmetric. It will still be banded. There's no. The third thing is that you have a symmetric matrix, and it will be singular, etc. You know, all those properties. As for this banded thing, to be precise, this banded nature won't be visible in the elemental matrices because they'll most probably be filled. They'll all be filled. But this banded nature comes out very visibly when you assemble them together, especially when you have made sure that you number the nodes in the shorter direction. We have covered this earlier, and if you do that, then the nodes that are away from you, at a certain point you will have a bandwidth here. So at a certain point, at a certain distance away, you will start having all the zeros here. So this banded thing will be very visible at that stage, not here, but when you follow this process of mapping, and if you have been careful in node numbering, then you'll also get a banded matrix. As for symmetry and singular, that is always there, and also those properties that if you add the numbers in all the rows and all the elements, they come out to be 0. Those are always there. And this is how you assemble the two stiffness matrices and all other stiffness matrices in the system, and you get the system matrix. Now this is one part of the assembly. There's another part very similar in nature, but let's go through that also. And that is the assembly of forces. You not only assemble K matrices, but you also assemble force vectors, and that is also a similar process. Let's say we have this force vectors for the second element and the seventh element. Now these force vectors are a result of body forces, pressure forces and thermal forces. They have to be. Now in some cases there will be no thermal forces or body forces, but these have the effects of body forces, pressure forces and thermal forces if there is a temperature change. Concentrated loads are not included here. They cannot be, because you recall from your previous experience that we only assemble, we only first at the elemental level we only make these F vectors which are corresponding to these three types of forces. We don't, if there is a concentrated load here, for example, or here, we don't add it at this stage. First we make the elemental matrices, then we assemble them, and we are going to do that. And finally at the very end, when you have the system F matrix, after assembly of this, then at the very end you just add at the relevant degree of freedom some concentrated force if it is applied. Because if you apply some concentrated force here at this stage, for example element 2 is corresponds to degree of freedom 3 and 4. So if you apply it on 3 or 4 degree of freedom here, and there is another element here, then again for that element you will also apply it there. Then when you assemble them, you'll get double of the forces, which is wrong. So we take that step at the very end. So for now we are just going to assemble these three forces. You assume that you have at the elemental level you have these prepared, and now you have to assemble them. We again go through the same process. First of all we number them, and the numbering will be exactly the same, because again you will be following the same scheme. It's a 2D system. The scheme will be 2i minus 1 and 2i. So you just put in the values of, and obviously for j and k also. This is I, this is j, this is k. Similarly, I, j, k. So what you do now is you just mark the degrees of freedom here like we did last time. So it's going to be the same 3, 4, 1, 2, 9, 10 because it's the same scheme 3, 4, 1, 2, 9, 10 and 7, 8, 9, 10, 1, 2. It's the same thing here, only we have just one dimension here 3, 4, 1, 2, 9, 10, 7, 8, 9, 10, 1, 2. And now when we assemble them together, it's very simply this. Again, you just first create a placeholder 1, 2, 3, 4, 5, 6, 7, 8. This is 10 degrees of freedom, at least we know. From 1 to 10, there are 1 to 10, and maybe some are missing, but there could be more. But for now, we know that at least 10 are there. So you just put in the values now 3 and 4. 3 and 4. This is 3 and 4 place. So you get this 3 and 6 here. Then 1 and 2. 4 and 1. Then you have 9 and 10. 7 and 5. So you have dealt with the force vector for element 2. Now for element 7. First of all, 9 and 7. They come 7 and 8 place. 7 and 8 place, 9 and 7. Now 9 and 10. 9 and 10 already you have values, but you just add them because both are common here. So 9 and 10, 6 and 2. So you have this plus 6 plus 2. Then 4 and 5 at 1 and 2 place. 4 and 5 at place 1 or 2. So you have dealt with this also. Now there are some zeros here. And why there are zeros here? Because if you see here, you have this 5 and 6. 5 and 6 would correspond to node number 3 here, but there's no node number 3 here. Maybe it's somewhere here or somewhere here. So sooner or later it will come here. So these zeros will be replaced by some numbers. But at this moment, you only have 1, 4, 5 and 2. So 3 is missing. So very appropriately, there are no values here. In other words, there are 0 values. And again, this because this corresponds to node number 3. Now again, you see wherever there is addition, these are the nodes 1, 2, 9 and 10. 1, 2, 9 and 10 because 1 and 2 nodes, 1 and 2 degrees of freedom are for node 1. Again, common node between the two elements. 9 and 10 again for node 5. Again common. Now 4 and 2, 4 these are 7 and 8. 2 nodes, it has 3 and 4. So 7, 8, 3 and 4, there is no addition. Maybe when you deal with this element, this one, so then you will have this also common. But at the moment there is only these common, so there are, it all makes sense. So here I must add and so on till all the elements have been assembled. We just shown 2 elements. So when you have assembled all the elements, then you have this F matrix, and then as a result of this, Ku is equal to F. At the very end, we just add concentrated load vector. For example, here there's a load F2x, F2y. So F2x and F2y would correspond to degree of freedom 3 and 4. Degree of freedom 3 and 4 because 2 corresponds to 3 and 4. So at this point, where this F matrix will have from 1 to 10, where 3 and 4, degree of freedom 3 and 4, you'll have this one matrix plus then you'll add concentrated load, and only here you'll have F2x and F2y just once. If you had done the same step at this point, then for this element you'll again would have considered these, and then if you had added them together, then you'll have maybe twice or 3 times because there's other elements also. So this step takes place at the very end. So when you get this is your Ku is equal to F, and these are system equations now, and you just solve them after applying the boundary conditions, which is the topic of the next lecture. Thank you very much.